Again, I want to remind you that in order to understand action potentials and graded potentials in neurons, you need to make sure that you understand the terms polarization, depolarization, and resting membrane potential, and how the flow of ions is related to those. So as we begin looking briefly at graded potentials, so these are small localized deviations from the resting membrane potential that makes the membrane either more polarized, so the inside becomes more negative, or less polarized, where the inside becomes less negative. When the stimulus causes the membrane to become more polarized, then that's said to be a hyperpolarizing potential, and of course we're looking at graded potentials, so a hyperpolarizing graded potential. When the stimulus causes the membrane to become less polarized or less negative on the inside, it's said to be a depolarizing graded potential. So a graded potential occurs when a stimulus causes ion gates, mechanical or ligand gated, to open or close in the cell's membrane. So the potential, of course, is going to change once those gates open and the flow of ions is allowed to come into or out of the cell. So to say that these electrical signals are graded simply means that they vary in amplitude, the size, depending on the strength of the stimulus. So they're larger or smaller depending on how many of those ion gates open or close and how long they stay open. So the opening or closing of these ion channels alters the flow of specific ions across the membrane. So it produces a flow of current that's localized in that particular part of the membrane. Now, once that membrane becomes depolarized in that particular area, it can spread to adjacent regions along that cell membrane in either direction from the initial stimulus, but only over a short distance, and then it gradually dies out. So because these potentials die out within just a few millimeters of their original point of the original stimulus, the graded potentials are useful only for short distant communication. And even though these graded potentials sort of die out over a period of time and over distance, they can become stronger and last longer by summating or adding together the stimulus from other graded potentials. So summation is the process by which graded potentials add together. So for instance, if two depolarizing graded potentials summate, the result is a larger depolarizing graded potential. If two hyperpolarizing graded potentials summate, the result is a larger hyperpolarizing graded potential. But what if two equal oppositely graded potentials summate, so one depolarizing and the other hyperpolarizing? Well, as you would assume, they cancel each other out, and the overall graded potential just disappears. And we'll talk more about summation in a little bit, but the importance of these graded potentials is that they are needed when they happen along the surface of those dendrites to stimulate the cell to create an action potential. An action potential or impulse is a sequence of rapidly occurring events that decrease and then eventually reverse the membrane potential and then restore it back to the resting state. An action potential has two main phases, a depolarizing phase and a repolarizing phase. During the depolarizing phase, the negative membrane potential becomes less negative, reaches zero, and then becomes positive. During the repolarizing phase, the membrane potential is restored to its resting membrane potential of about negative 70 millivolts. A few important facts to keep in mind as we look at action potentials. Remember, this is a brief reversal of membrane potential. Unlike graded potentials, an action potential does not decrease in magnitude over distance. An action potential is generated and propagated, or basically moved down the cell along an axon, and the transition from graded potentials to action potentials takes place at the axon hillock. Now remember when we did neuron structure back a couple of lectures ago, we looked at the processes coming off the cell body or the soma, and we saw the dendrites were the receivers, and then the cell body was going to process that depolarization, and as that depolarization moves along the cell body, it then reaches the area called the axon hillock, so that sort of cone-shaped area, and it's at that point where if depolarization is enough, then an action potential is fired. Now when I say depolarization is enough, that simply means that the membrane potential has reversed to enough difference in charge. Here we're looking at a graphical representation of an action potential. So when a cell is at rest, and we're looking at a nerve cell, of course, you have a charge of negative 70 millivolts inside the cell. So we're looking at the resting membrane potential. Now, when we look at this graph, we see the voltage and a difference in time. So we're looking at what's happening with the charges inside that cell over a period of time in response to a stimulus. So here the cell is resting at negative 70 millivolts, and a stimulus occurs. Remember, the stimulus is going to cause those ion gates to open. When the ion gates open, the cell depolarizes as those positively charged ions come in. Now, the reason that cell is depolarizing is because the graded potentials of that initial stimulus opened enough gates for enough positively charged ions to come in that the cell depolarized to the threshold level. So threshold is simply the minimum depolarization that has to occur in order for that cell to fire an action potential or a nerve impulse. Okay? So the stimulus came in, the cell depolarized to threshold, and then the axon hillock fired an action potential along that axon. Now, once the action potential reaches the axon terminal, the neurotransmitter has been released, then that action potential is done. So the cell has to repolarize, which means we have to get it back to normal. We've got to get it polarized again. So we do so by pumping out those positively charged ions, but oops, we get to an area where we overshoot a little bit, and that is a time we call a refractory period. A refractory period is a time where the cell just can't respond again because it hasn't gotten back to normal yet. Okay, when the cell gets back to normal, it's back to its resting state of negative 70 millivolts. So a couple of things I want to point out here. This refractory period I often describe as sort of analogous to flushing your toilet. Think about what happens when you flush your toilet. The water goes out, and then the tank has to refill again before you can flush it again. So you can sit there and wiggle, 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 wiggle all you want to on that handle, but the toilet is not going to flush. The toilet's not going to flush until what? The toilet gets back to its refilled normal state again. Well, that's the same thing that's happening with these cells. They have to repolarize, get back to the normal state of polarization before they can fire again. So that's your refractory period. The other thing I wanted to bring up here is this subthreshold stimulus. So if a stimulus is not strong enough to cause enough depolarization, then that action potential is not going to fire. So as we look at the steps of generating an action potential, we begin with the resting state, where all the voltage-gated sodium and potassium gates are closed, the leakage channels are open, the cell membrane of the axon is at resting membrane potential, We have a small buildup of negative charges along the inside of the membrane, an equal number of buildup of positive charges on the outside of the membrane. We have more sodium in the extracellular fluid, more potassium on the intracellular fluid, and the cell is ready to do something because of that resting membrane potential. When a depolarizing graded potential or some other stimulus causes the membrane of the axon to depolarize to threshold, voltage-gated sodium channels open very quickly. So both the electrical and the chemical gradients favor the inward movement of sodium, so the resulting inrush of positively charged sodium ions causes the depolarization phase of the action potential. So all those positively charged sodium ions change the membrane potential from about negative 55 millivolts to positive 30 millivolts. At the peak of the action potential, the inside of the membrane is 30 millivolts more positive than the outside. As more and more channels open, more and more sodium inflow, or more and more sodium flows in, the membrane depolarizes further and causing even more sodium channels to open. So this is an example of a positive feedback mechanism. Once the action potential has fired, the cell has to undergo a repolarization period. This is the time where the sodium gates have closed, so sodium is no longer rushing into the cell, but potassium gates open. So potassium rushes outside of the cell, and of course potassium being positively charged, that's going to restore the electronegativity inside the cell. So it sort of corrects the electrical gradient, getting the cell back toward that resting membrane potential. However, the cell goes through a period when the calcium or the potassium gates are open, and the outflow of potassium is enough to cause a hyperpolarization phase of the membrane. So we call that a part of the refractory period during which the cell can no longer respond. So the cell becomes even more electronegative, where the membrane potential may dip down to a negative 90 millivolts as excessive potassium ions are pumped out. So during this time, when we do have the refractory period, of course, we break that period down into an absolute and a relative refractory period. So it's the period of time after an action potential that an excitable cell, a neuron, can't regenerate another action potential in response to a normal threshold stimulus. So during the absolute refractory period, the cell absolutely can't respond to even a very strong stimulus to initiate a second action potential. So this period is when the sodium channels have closed, and the sodium channels then can't reopen until that membrane returns back to its resting membrane potential. During the refractory or the relative refractory period, a second action potential can be initiated, but only by a larger than normal stimulus. So this is the time when the voltage-gated potassium channels are still open, even after the sodium channels have returned to their normal resting state, so they can open again as well. Okay, so at the top of this one you see a warning. I know it's a very wordy slide, but I tried to cut it down as much as I could and still have all the information in there. So here we see that initial graph that we looked at, and yes, I know it's very small. You may want to look back at the other one, but we had the resting membrane potential, then the stimulus came in, caused depolarization, then repolarization, hyperpolarization, and back to resting membrane potential. So let's look at the membrane and see what's happening here. In step 1, during the resting state, sodium and potassium ions are not passing through the membrane except through those leak channels, and overall there is a more electronegative charge on the inside of the cell. So these little green balls here are sodium ions. The little purple triangles down here are potassium ions, okay? So here we've got a sodium-potassium pump, and we've got a potassium channel and a sodium channel. All right, so an action potential has occurred. Step 2. Once that action potential is triggered, depolarization of the membrane happens as sodium ions with their positive charges come into the cell. That causes the cell to depolarize as those positively charged ions come in. In step 3, the cell membrane has to repolarize. So you can see now the sodium channel is closed, the potassium channel is open. So that potassium channel, of course, is going to move those potassium ions, positively charged potassium ions, out into the extracellular fluid, resulting in the cell becoming more electronegative. It overshoots a bit and allows that cell to become hyperpolarized. And then in step 4, we have to return things back to normal. So to get that cell back to the resting membrane potential, a sodium-potassium pump is going to exchange 3 sodiums for every 2 potassiums. So getting those sodium ions out and potassium ions back in to reset that membrane back to resting membrane potential so the cell can respond to the next action potential. One more slide just to reinforce the idea of the action potential moving along that axon. Remember, the cell was at its resting membrane potential. A stimulus was brought into the cell, so the dendrites perhaps received that stimulus and they started producing graded action potentials all along the cell membrane. Remember, dendrites are extensions of the cell membrane, so that membrane depolarizes in those graded potentials that then starts to depolarize the membrane of the cell body. Once that reaches the area of the axon hillock, if the stimulus was enough to cause depolarization enough to the threshold level, that action potential fires down the axon. Remember, the axon is also made of cell membrane. So depolarization, 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 depolarization all along that axon membrane down to the axon terminals, which are still made of cell membrane, cell membrane. So they're depolarizing, depolarizing until that action potential reaches the axon terminals, or the little synaptic knobs where the neurotransmitters may be released. Now this brings up the term of repolarization chases depolarization. So as we talked about on the previous slide, once an area of the membrane has depolarized, then those sodium gates close and the potassium gates open, so that particular area of the membrane repolarizes. So repolarization is said to chase depolarization in that it follows depolarization down the axon. So an area that has already depolarized begins to repolarize.